NLP techniques in large language models, foundations, advanced methods, and future directions. Large language models, LLMs, have emerged as a transformative force in the field of natural language processing, NLP, pushing the boundaries of what is possible in machine understanding and generation of human language. These models, characterized by their immense scale and sophisticated architectures, have demonstrated remarkable capabilities across a wide range of NLP tasks, often matching or surpassing human performance. At the heart of LLMs lie a variety of NLP techniques that enable these models to process, understand, and generate human language with unprecedented proficiency. These techniques range from fundamental methods for text processing to advanced approaches for transfer learning and few-shot adaptation. Understanding these NLP techniques is crucial for grasping the full potential and limitations of LLMs in various applications. This paper aims to provide a focused review of the key NLP techniques employed in large language models. We will explore the foundational methods that form the basis of LLM architectures, examine advanced techniques that enhance their capabilities, and discuss how these methods are applied to various NLP tasks. Furthermore, we will consider the challenges and limitations of current approaches and look towards future directions in this rapidly evolving field. By offering an in-depth analysis of NLP techniques in LLMs, this paper seeks to serve as a valuable resource for researchers, practitioners, and enthusiasts in the field of natural language processing and artificial intelligence. It provides insights into the technical underpinnings of these powerful models, while also considering their broader implications for the future of NLP and AI at large. Large language models build upon a foundation of NLP techniques that enable them to process and understand human language effectively. These foundational techniques form the building blocks upon which more advanced capabilities are constructed. Tokenization, the process of breaking down text into smaller units or tokens, serves as the first step in text processing for LLMs. While traditional NLP systems often relied on simple word-level or character-level tokenization, LLMs typically employ more sophisticated methods. Subword tokenization has emerged as a particularly effective approach for LLMs. Methods such as byte pair encoding, BP, and word piece break words into smaller units, allowing the model to handle rare words and morphological variations more effectively. For example, BP iteratively merges the most frequent pair of bytes or characters to build a vocabulary of subword units. This approach strikes a balance between the flexibility of character-level tokenization and the semantic meaningfulness of word-level tokenization. Another notable tokenization method is sentence piece, which treats the input text as a sequence of Unicode characters. This unsupervised text tokenizer and detokenizer can learn to tokenize any language without requiring language-specific preprocessing, making it particularly useful for multilingual models. These advanced tokenization methods enable LLMs to work with a manageable vocabulary size while still capturing the nuances of language and handling out-of-vocabulary words effectively. The representation of words and tokens is a critical aspect of LLMs. While earlier NLP models used static word embeddings like word2vec or gloV, LLMs leverage contextual representations that capture the nuanced meanings of words based on their surrounding context. In LLMs, each token's representation is typically a function of the entire input sequence, computed through multiple layers of self-attention and feed-forward neural networks. This allows the model to capture word-sense disambiguation and handle polysemy more effectively. For instance, the representation of the word bank would differ depending on whether it appears in the context of a financial institution or a river bank. These contextual representations enable LLMs to achieve a much deeper understanding of language, capturing subtle differences in word usage and meaning across different contexts. Attention mechanisms are at the core of transformer-based LLMs, allowing models to focus on relevant parts of the input when processing or generating text. Self-attention, a key innovation in transformer architectures, allows each token in a sequence to attend to all other tokens, capturing relationships regardless of their distance in the sequence. This enables LLMs to handle long-range dependencies more effectively than previous architectures that relied on recurrent or convolutional neural networks. Multi-head attention extends self-attention by allowing the model to attend to information from different representation subspaces simultaneously. This enables the model to capture various types of dependencies within the data, enhancing its ability to understand complex linguistic structures. Unlike recurrent neural networks, transformer models do not inherently capture the order of tokens in a sequence. To address this, LLMs use positional encodings to inject information about the relative or absolute position of tokens. Positional encodings can be implemented using fixed mathematical functions, often sine and cosine functions, or learned during the training process. These encodings ensure that LLMs can distinguish between different arrangements of the same words, enabling them to understand and generate grammatically correct and coherent text. These foundational NLP techniques form the basis upon which LLMs build their impressive language understanding and generation capabilities. In the next section, we will explore more advanced NLP techniques that further enhance the abilities of these models. Building upon the foundational techniques, large language models incorporate a variety of advanced NLP methods that significantly enhance their capabilities. These techniques enable LLMs to adapt to new tasks, generalize across languages, and perform well even with limited task-specific data. Transfer learning has become a cornerstone of modern NLP, allowing models to leverage knowledge gained from one task or domain to improve performance on others. This approach is particularly powerful in the context of LLMs due to their vast knowledge acquired during pre-training. The pre-training and fine-tuning paradigm is central to many LLMs. During pre-training, models learn general language understanding from vast amounts of unlabeled text data, often using objectives such as masked language modeling or next sentence prediction. This general knowledge can then be adapted to specific tasks through fine-tuning on smaller, specialized datasets. Domain adaptation techniques allow LLMs to be tailored for particular areas such as legal, medical, or scientific text. This can involve additional pre-training on domain-specific corpora or careful fine-tuning strategies. The result is models that can capture domain-specific vocabulary, writing styles, and knowledge while retaining their broad language understanding. One of the most impressive capabilities of advanced LLMs is their ability to perform tasks with little or no task-specific training data. Few-shot learning allows models to learn new tasks from just a handful of examples, while zero-shot learning enables models to perform tasks they were not explicitly trained on, given only a natural language description of the task. These capabilities are often achieved through clever use of prompts and in-context learning. By formulating tasks in a specific way within the input prompt, LLMs can be guided to perform a wide range of tasks without the need for explicit fine-tuning. Prompt engineering has emerged as a crucial technique for extracting optimal performance from LLMs. By carefully crafting the input prompt, researchers and practitioners can guide the model's behavior and improve its performance on specific tasks. In-context learning refers to the ability of LLMs to adapt their behavior based on examples provided within the input context. This allows for dynamic task specification and enables models to perform new tasks without the need for gradient updates or fine-tuning. Advanced LLMs have made significant strides in multilingual and cross-lingual capabilities. Models like MUT, Multilingual BERT, and XLMR are pre-trained on text from multiple languages, developing a shared representation space across languages. These multilingual models enable zero-shot cross-lingual transfer, where a model fine-tuned on a task in one language can perform the same task in other languages without additional training. This capability has important applications in low-resource language processing and in developing more inclusive global NLP systems. Techniques such as language-agnostic sentence encoders and cross-lingual pre-training objectives have further enhanced the ability of LLMs to operate across language boundaries. These advanced NLP techniques have significantly expanded the capabilities of LLMs, enabling them to adapt to new tasks and domains with unprecedented flexibility. In the next section, we will explore how these techniques are applied to various NLP tasks within the context of large language models. Large language models have demonstrated remarkable proficiency across a wide range of NLP tasks. This section explores key NLP tasks and the specific techniques employed by LLMs to address them. Text generation is one of the most prominent applications of LLMs. At their core, many LLMs are trained on the task of predicting the next token in a sequence given the preceding context. This fundamental capability underlies more complex text generation tasks. Decoding strategies play a crucial role in generating coherent and diverse text. Beam search maintains multiple potential output sequences and selects the most probable one, often resulting in high-quality but potentially repetitive text. Nucleus sampling, also known as top P sampling, samples from the top tokens that cumulatively exceed a probability threshold, balancing quality and diversity in generated text. Controlled text generation techniques allow for more fine-grained control over the attributes of the generated text, such as style, tone, or content. Methods like conditional language models and attribute classifiers enable the generation of text with specific desired characteristics. LLMs have shown impressive capabilities in identifying and classifying named entities in text. The contextual understanding of LLMs allows them to disambiguate entities based on surrounding context, improving accuracy over traditional NER systems. For information extraction tasks, LLMs can be fine-tuned to identify specific types of information within text, such as events, relationships between entities, or key facts. Techniques like span prediction and sequence labeling are often employed for these tasks. LLMs excel at tasks like sentiment analysis and text classification due to their nuanced understanding of language. Fine-tuning LLMs on specific classification tasks often yields state-of-the-art results. Techniques such as prompt-based classification, where the classification task is reformulated as a text generation problem, have shown promising results. For instance, instead of using a traditional classification head, the model might be prompted to generate positive or negative based on the input text. In the domain of machine translation, LLMs have pushed the boundaries of what's possible. Techniques like sequence-to-sequence learning with attention mechanisms form the basis of many LLM-based translation systems. Multilingual LLMs enable zero-shot translation between language pairs not seen during training. Techniques like pivoting through a high-resource language and back translation have further improved translation quality, particularly for low-resource language pairs. LLMs have revolutionized question-answering systems, enabling more natural and context-aware responses. Techniques like span prediction, where the model identifies the span of text in a given context that answers the question, are commonly used. For open domain question answering, LLMs leverage their broad knowledge base acquired during pre-training. Retrieval-augmented generation techniques, which combine information retrieval with text generation, have shown promising results in improving the factual accuracy of responses. LLMs can generate both extractive summaries, selecting key sentences from the original text, and abstractive summaries, generating new sentences that capture the essence of the original content. Techniques like fine-tuning on summarization datasets, using special tokens to control summary length, and employing reinforcement learning to optimize for summary quality have all contributed to improving the summarization capabilities of LLMs. In the realm of dialogue systems, LLMs have enabled more natural and context-aware conversations. Techniques like dialogue state tracking, response generation, and context modeling allow LLMs to maintain coherent conversations over multiple turns. Approaches such as persona-based dialogue generation, where the model is conditioned on a specific persona or character, have improved the consistency and personality of conversational agents. These applications demonstrate the versatility of LLMs across a wide range of NLP tasks. In the next section, we will explore techniques for enhancing the capabilities of LLMs, addressing some of their current limitations and challenges. While large language models have demonstrated impressive capabilities, there are ongoing efforts to enhance their performance, reliability, and applicability. This section explores various NLP techniques aimed at improving different aspects of LLMs. One of the challenges faced by LLMs is ensuring factual accuracy and consistency in their outputs. Several techniques have been developed to address this issue. Knowledge integration methods aim to incorporate structured knowledge into LLMs. Techniques like entity linking, where mentions in the text are linked to entries in a knowledge base, can improve the factual grounding of model outputs. Retrieval-augmented generation approaches combine the generative capabilities of LLMs with explicit retrieval of relevant information. This can help in providing more accurate and up-to-date information, especially for queries requiring specific factual knowledge. Fact-checking mechanisms, where model outputs are verified against reliable sources, are being explored to improve the trustworthiness of LLM-generated content. Addressing bias in LLMs is a critical area of research. Several NLP techniques are being employed to mitigate various forms of bias. Data augmentation and balancing techniques aim to create more representative training datasets, reducing bias at the source. Debiasing methods applied during or after training attempt to reduce learned biases. These can include adversarial debiasing techniques or post hoc methods that adjust model outputs to be more neutral. Controlled generation techniques allow for specifying desired attributes of the generated text, potentially enabling the generation of less biased content. The complexity of LLMs often makes it challenging to interpret their decision-making processes. Several techniques are being developed to address this. Attention visualization methods aim to provide insights into which parts of the input the model is focusing on when making predictions or generating text. Probing tasks, where auxiliary classifiers are trained to predict specific linguistic properties from model representations, can help in understanding what information is captured at different layers of the model. Explanation generation techniques, where the model is trained to provide natural language explanations for its outputs, are being explored to make LLM decisions more transparent and understandable to users. Enhancing the reasoning and abstraction capabilities of LLMs is an active area of research. Integration of symbolic reasoning techniques with neural approaches aims to combine the strengths of rule-based systems with the flexibility of LLMs. Multitask learning approaches, where models are trained on a diverse set of tasks requiring different types of reasoning, can potentially improve the model's general reasoning capabilities. Common sense knowledge injection techniques attempt to incorporate everyday knowledge that humans take for granted into LLMs, improving their ability to reason about everyday scenarios. These techniques represent ongoing efforts to address some of the current limitations of LLMs and to enhance their capabilities across various dimensions. As research in this area continues, we can expect further advancements in the reliability, interpretability, and reasoning capabilities of large language models. In the next section, we will explore the methods and challenges involved in evaluating and benchmarking these enhanced LLM capabilities. As large language models continue to advance in capabilities and complexity, the methods for evaluating and benchmarking these models have become increasingly important. Proper evaluation not only helps in tracking progress in the field but also ensures the reliability and applicability of these models in real-world scenarios. Numerous benchmarks have been developed to evaluate the performance of LLMs across various NLP tasks. GLUE, General Language Understanding Evaluation, and its more challenging counterpart superglue provide a collection of diverse tasks designed to test natural language understanding capabilities. These include tasks such as sentiment analysis, question answering, and textual entailment. SQUAD, Stanford Question Answering Dataset, focuses on reading comprehension and question answering abilities, requiring models to locate answers within given passages of text. Lambda, Language Model Benchmark on Close-Style Task, tests the model's ability to understand broader context by predicting missing words in carefully selected passages. WMT, Workshop on Machine Translation, provides benchmarks for evaluating machine translation performance across various language pairs. These benchmarks provide standardized datasets and evaluation metrics, allowing for consistent comparison across different models and approaches. However, as models continue to improve, there is an ongoing need to develop more challenging and diverse benchmarks that can effectively differentiate between advanced LLMs. Different NLP tasks require specific evaluation metrics to accurately assess model performance. For classification tasks, metrics such as accuracy, precision, recall, and F1 score are commonly used. The choice of metric often depends on the specific requirements of the task and the balance of the dataset. In generation tasks like machine translation or text summarization, metrics such as blur, rouge, and meteor are frequently employed. These metrics attempt to quantify the similarity between model-generated text and human-written references. However, they have limitations in capturing semantic similarity and overall quality. For question-answering tasks, metrics like exact match, EM, and F1 score are often used to evaluate the overlap between predicted answers and ground truth. In language modeling tasks, perplexity remains a standard metric, measuring how well a model predicts a sample of text. For dialogue systems, evaluation often involves a combination of automated metrics, for example, response relevance, diversity, and human evaluation of factors like coherence and engagement. Evaluating large language models presents several unique challenges. Scale and computational requirements. The sheer size of LLMs makes comprehensive evaluation computationally expensive and time-consuming. Generalization versus memorization. It can be difficult to distinguish whether an LLM is truly generalizing or merely recalling information from its training data. Contextual understanding. Evaluating an LLM's understanding of context, especially over long passages or dialogues, remains challenging. Creativity and open-ended tasks. For tasks involving creative generation or open-ended responses, automated evaluation metrics often fall short, necessitating human evaluation. Ethical considerations. Evaluating the ethical implications of LLM outputs, such as potential biases or harmful content, is crucial but challenging to quantify. Robustness and consistency. Assessing an LLM's performance consistency across different prompts or phrasings of the same task is important but often overlooked in standard benchmarks. To address these challenges, researchers are exploring more comprehensive evaluation frameworks that combine automated metrics with human evaluation, adversarial testing to probe model limitations, and the development of more nuanced benchmarks that can capture the multifaceted capabilities of LLMs. As the field continues to advance, the development of more sophisticated, comprehensive, and fair evaluation methods will be crucial in guiding future research and ensuring the responsible deployment of LLMs in real-world applications. Despite their impressive capabilities, large language models face several significant challenges and limitations. Understanding these constraints is crucial for researchers, developers, and users of LLM technologies. One of the most prominent challenges associated with LLMs is their immense computational resource requirements. Training large models requires substantial computational power, often necessitating large clusters of GPUs or TPUs. This results in significant financial costs and limits the ability of many researchers and organizations to develop or replicate these models. Inference, while generally less resource-intensive than training, can still present challenges for real-time applications, particularly those requiring low latency. The energy consumption associated with training and running large models has raised concerns about their environmental impact, prompting research into more efficient architectures and training methods. While transformer-based architectures have improved the ability of models to capture long-range dependencies, limitations still exist. The standard self-attention mechanism scales quadratically with sequence length, making it computationally infeasible to process very long documents. Even when processing long sequences is computationally possible, models often struggle to maintain coherence and consistency over extended contexts. Techniques like sparse attention, sliding window attention, and hierarchical approaches have been proposed to address these issues, but handling truly long-range dependencies remains an active area of research. While LLMs have shown impressive language understanding and generation abilities, they still face challenges in tasks requiring complex reasoning, or abstraction. Common sense reasoning, especially involving implicit knowledge that humans take for granted, remains difficult for current models. Multi-step logical reasoning, as required in mathematical problem-solving or complex decision-making scenarios, is an area where LLMs often fall short. Abstraction and generalization beyond the patterns seen in training data can be challenging, leading to difficulties in handling novel scenarios or combinations of concepts. The development and deployment of LLMs raise several ethical concerns. Bias and fairness. LLMs can perpetuate or amplify societal biases present in their training data, leading to unfair or discriminatory outputs. Privacy concerns. The use of vast amounts of text data for training raises questions about data privacy and the potential for models to memorize and reproduce sensitive information. Misinformation and malicious use. The ability of LLMs to generate human-like text raises concerns about their potential misuse for creating misinformation or deepfake text. Transparency and explainability. The complexity of LLMs often makes it challenging to interpret their decision-making processes or explain their outputs, which can be problematic in applications requiring accountability. Environmental impact. The substantial computational resources required for training and running LLMs have raised concerns about their carbon footprint. Addressing these ethical considerations requires a multidisciplinary approach, involving not just technologists but also ethicists, policymakers, and other stakeholders. These challenges and limitations highlight the areas where current NLP techniques in LLMs fall short and point to important directions for future research and development. In the next section, we will explore some of these future directions and emerging approaches aimed at addressing these limitations. The field of large language models is rapidly evolving, with new advancements and research directions emerging regularly. This section explores some of the most promising avenues for future development in NLP techniques for LLMs. As concerns about the computational cost and environmental impact of LLMs grow, there is a strong push towards developing more efficient models. Sparse models. Research into sparse attention mechanisms and conditionally activated networks may lead to models that use fewer parameters more efficiently. Distillation and compression. Techniques for distilling knowledge from large models into smaller, more efficient ones without significant performance loss are being actively explored. Adaptive computation. Developing methods for models to dynamically adjust their computational depth based on the complexity of the input could lead to more efficient inference. Hardware-software co-design. Closer integration of model design with specialized AI hardware could significantly improve efficiency. The future of LLMs likely involves more seamless integration of multiple modalities. Vision language models. Advancing beyond current image captioning and visual question answering to deeper integration of visual and linguistic understanding. Audio-text integration. improved capabilities in speech recognition, text-to-speech, and understanding the relationship between spoken and written language. Multimodal reasoning, developing models that can reason across different modalities, combining information from text, images, audio, and potentially other sensory inputs. Combining the strengths of symbolic AI with the flexibility of neural networks is a promising direction. Neurosymbolic AI, integrating neural network approaches with symbolic reasoning techniques could lead to models with improved logical reasoning capabilities and interpretability. Knowledge graph integration, more tightly coupling language models with large-scale knowledge graphs could enhance their factual accuracy and reasoning abilities. Formal logic in neural networks, incorporating principles from formal logic into neural architectures might improve the model's ability to perform complex, multi-step reasoning. Emerging computing paradigms offer new possibilities for NLP and LLMs. Neuromorphic computing, hardware designed to mimic biological neural networks, could potentially enable more energy-efficient implementations of language models. Quantum NLP, while still in its early stages, quantum computing could potentially offer new approaches to certain NLP tasks, particularly in areas like semantic analysis and knowledge representation. Brain-inspired architectures, drawing inspiration from neuroscience to develop new model architectures that more closely mimic human language processing. These future directions represent exciting possibilities for advancing NLP techniques in large language models. As research progresses in these areas, we can expect to see LLMs that are more efficient, capable of handling multiple modalities, better at reasoning and abstraction, and potentially leveraging new computing paradigms. Natural language processing techniques in large language models have undergone remarkable advancements in recent years, fundamentally transforming our approach to a wide range of language-related tasks. Through this focused review, we have explored the evolution of NLP techniques within the context of LLMs, from foundational methods to advanced capabilities and their applications across various NLP tasks. The core NLP techniques employed in LLMs, such as sophisticated tokenization methods, contextual embeddings, and attention mechanisms, have enabled these models to capture the nuances and complexities of human language with unprecedented accuracy. The advanced capabilities that emerge from these foundations, including transfer learning, few-shot learning, and multilingual performance, have expanded the boundaries of what is possible in artificial intelligence systems. LLMs have demonstrated remarkable proficiency across a diverse array of NLP tasks, from text generation and understanding to complex question answering and dialogue systems. Their impact is felt across industries, from improving search engines and recommendation systems to enabling more natural human-computer interactions through conversational AI. However, the rise of LLMs also brings significant challenges. The computational resources required for training and deploying these models raise important questions about accessibility and environmental sustainability. Issues of bias, fairness, and the ethical implications of powerful language models remain active areas of concern and research. Moreover, the limitations in reasoning capabilities and handling long-range dependencies highlight the ongoing need for refinement and development in these systems. Looking to the future, the field of NLP in LLMs promises continued innovation. Advancements in multimodal learning, improved efficiency, and enhanced reasoning capabilities may lead to even more powerful and versatile language models. The integration of symbolic AI approaches with neural methods and the exploration of new computing paradigms like neuromorphic and quantum computing offer intriguing possibilities for the next generation of NLP techniques. In conclusion, NLP techniques in large language models represent a transformative force in the field of artificial intelligence. As we continue to refine and expand their capabilities, LLMs have the potential to drive further breakthroughs in our ability to process, understand, and generate human language. The ongoing research and development in this field will undoubtedly continue to shape the future of human-computer interaction and our understanding of language itself. However, as these models become more powerful and pervasive, it is crucial that their development be guided by careful consideration of their broader impacts. The ethical challenges and potential societal effects of LLMs demand ongoing dialogue and collaboration between technologists, ethicists, policymakers, and the broader public. Ensuring that these powerful tools are developed and deployed in ways that benefit humanity while mitigating potential harms will be one of the critical challenges in the coming years. As we stand at this exciting juncture, it is clear that the future developments in NLP techniques for LLMs will not only push the boundaries of what is technologically possible but also prompt us to grapple with fundamental questions about the nature of language, intelligence, and the evolving relationship between humans and AI. The story of NLP in large language models is, in many ways, a reflection of our ongoing quest to understand and replicate one of the most quintessential human abilities, the use of language. As this story continues to unfold, it promises to be one of the most captivating and consequential narratives in the history of artificial intelligence.